So this time we'll talk about learning from and for knowledge bases. So knowledge bases are basically structured databases of knowledge, usually containing something like entities, which are represented as nodes, relations, which are represented as edges between nodes. And there's kind of two questions here. One is, how can we learn to create or expand these knowledge bases with neural networks? So this is kind of relation extraction. And then the other question is, how can we learn from the information in knowledge bases to improve our neural representations or improve our neural methods? So in terms of types of knowledge bases, there's lots and lots of these. I think people may be familiar with WordNet. WordNet is a large database of words, including parts of speech, semantic relations, etc. So you have artifact on top, and then motor vehicle, motor car, go-kart, gas guzzler, etc. And it expresses is-a relations, part of relations, type instance, and it also has a type instance distinction. So this is a type. So president is a type, and then instance would be Trump or Obama or Bush or Clinton or whatever. It also has verb relations, so ordered by specificity, which is communicate and then talk and then whisper. It has adjective relations, mainly antonyms, so wet and dry, etc. So this is very useful. As I said at the very beginning of the class, people use these very widely, and then word embeddings came around, and word embeddings have now taken the place of a lot of the stuff we got from WordNet, but still it's not quite as rich as this knowledge base. Also, one other thing that WordNet has is it has different senses of words. So if you're word embeddings, usually we don't use multiple senses in most cases, but WordNet has multiple senses. Another database, which I believe is called Psych. I actually don't know the correct pronunciation, but I think that's right. Have people heard of this? A few people? Okay. So Psych is actually this massive project. It's a manually curated database attempting to encode all of common sense knowledge. It was 30 years in the making, and apparently 2 years ago they finally finished. So now they have encoded all of common sense knowledge. On their site, they say, they don't say that in quite strong terms, but they say we are now confident that our database is complete enough to be used in practical applications. So there you go. And you have things like thing, intangible thing, etc. And it's this big, huge hierarchy of knowledge, relations, rules, exceptions, etc. Unfortunately, this is commercial, so you can't just go and download it. You need to pay them to use it, but it was a very ambitious project. So fast forwarding 12 years from the paper. We also have DBpedia. So DBpedia is moving from manual creation of databases to extraction of structured data from Wikipedia. So Wikipedia, as you know, has these info boxes, Carnegie Mellon University. You have all your former names, you have your motto, you have your type, and you have when it's established. And all of this data is in kind of structured format, so you can just go in and crawl the Wikipedia pages and pull all this data out, turn it into a structured database. There's other things in this vein, like Yago. So Yago is a meta-knowledge base combining information from multiple sources, including Wikipedia, WordNet, etc. And it has expansions to cover temporal and spatial information. And BabelNet is like Yago. It's a metadatabase that includes various sources, such as WordNet and Wikipedia. But it's also augmented with multilingual links across things. So you have stuff like Balloon in lots of different languages, and all of these are within the same synonym set you have Wikipedia sentences that correspond to this, etc., links between them. So you can see this community of knowledge representation is kind of a separate community than NLP. It's kind of a separate set of people who do this, but they are very serious about doing this, and they create good resources with broad coverage and in various things, in various kind of intuitive ways. Then perhaps the most famous one, Freebase, was a curated database of entities which was linked in extremely large scale. They did this through things like crowdsourcing and community editing. And this has all kinds of things like both extracted from Wikipedia and manually added in check, etc. And then finally, moving a bit forward, now there's Wikidata. It's a knowledge base run by the Wikimedia Foundation, and Freebase, which was originally run by a company then bought by Google. Google basically donated it to Wikidata. So now Wikidata is kind of the successor of Freebase in a way. It incorporates many of the good points of the previous work, multilingual, automatically extracted, curated, and it has an interface using something called SparkQL, which is like a SQL for knowledge bases. So I blew through a whole bunch of these. The reason why I blew through them is because I figure if you're interested, then you can go and read more. If you're not interested, then you're not interested. So these are some of the resources that are out there. I'd say in NLP, the most common ones are Freebase and maybe WordNet, although you see people using the other ones as well. Yeah.
Is Wikidata like a superset of Freebase, or do they contain this strategy?
So that's a good question. My understanding until very recently was yes. So Wikidata was called the successor of Freebase, and my understanding was that they donated all of Freebase to Wikidata. Recently, I heard from somebody that that might not be the case, so I only have about 90% confidence when I say yes, but I'm not 100% sure. Any other questions? Yeah.
Called ConceptNet.
ConceptNet? Okay, and what is the relationship to that?
It's also a knowledge base.
Okay.
Yeah, Faruqui is a relationship.
Okay. Yeah, I haven't been aware of a lot of people using it, but yeah.
There's also the NL dataset, right? Which is just relations.
Right, yes. So there's an L data set. There's also something called Reverb. OpenIE. So yeah, there's a lot, and I wasn't able to cover all of them here, but there are definitely those ones as well. So if you're interested, could you briefly summarize the like?
NL, OpenIE, all generations, ConceptNet. There is UMLS for medical data.
Mm-hmm.
There is Kinship for understanding relations in general.
Yeah. So.
Freebase, different versions of those.
So there's lots and lots of these. The NL one and Reverb are both kind of very heavy on the automatically extracted aspect as opposed to being extracted from structured data or being manually curated. So the ones I listed here are all ones that are basically, you can more or less assume that they're correct because they were either extracted from from structured data that was curated or they were directly curated themselves. So there's also really large scale ones like NL and Reverb, and these are ones that were automatically extracted, so they're not quite as like reliable in the data. So okay, so the next thing I'm going to talk about is relation extraction. This was the topic of the reading, but I'm going to talk about it from the neural perspective. So one of the problems about knowledge bases is that knowledge bases are always incomplete. They are very, very even the very, very big ones are incomplete. And this is basically, it's impossible to get them to be complete. And the reason why is let's say you add more humans to the knowledge base to increase its coverage. Suddenly you need to give all the information about these humans, like where did they go to college? And even if you say where did people go to college is something that you might not necessarily have, it's pretty certain that all humans were born at some point. Yet in Freebase, 71% of humans are missing their date of birth. So you can see that only 29% of people we know when they were born. So the idea is, if we have lots of data, can we perform relation extraction to extract information to fill up these knowledge bases? So doing this with neural networks, the main tool that we have, and it's a very useful tool, is the fact that we have consistency in embedding space. So if we have, this is a graph that everybody's, or the figure that everybody's seen before, where you can go from king to kings and queen to queens, and they both have the same relation, so they have the same, more or less the same vector in space. So I don't know if this is necessarily the first, but one of the first major works on this was relation extraction with neural tensor networks. So the idea is that we have a multi-layer perceptron that basically predicts whether a relation exists. Or we have a neural network that predicts whether a relation exists. And the first thing we can do is basically take a multi-layer perceptron, feed in the embeddings for the left for one entity and another entity, and predict whether a relationship exists between them. So you'd feed in the embedding for Barack Obama and President of the U.S. and see whether this relation, Barack Obama and President and United States. So as we know, relations are triples where you have two entities in the type. So then you have basically for each relation R, you have parameters for this multi-layer perceptron. So this paper expands on this a little bit. They use a neural tensor network which adds bilinear feature extractors, which are projections in space. So this part here, this part over here is basically equivalent to the thing up top, but they also add a bilinear function where you take the entity and you multiply it by a matrix, and then you take the other entity. And the reason why this is good is because basically what this is saying is we're taking entity 2, we're projecting it into a new place in space, and then we're finding out how close it is to the other entity. So that exactly follows our intuition here, right? It follows our intuition that if you take kings, you project it into another place. If you take king and project it into another place in space, it should be close to kings. And then if you do the same projection between queen and queens, they should be close together as well. And specifically by close together, I mean their dot product is high. So yeah.
What's the intuition behind taking k different projection matrices for each pair?
Let me see. That is because you want to extract as many features from this as you extract. Yeah. So So that's actually an important point. Sorry, I skipped this. So this is important, and it actually explains why the other ones are necessary next time. So what this is actually doing, I'm sorry, it's not a matrix. It's actually a tensor, where the tensor is the size of the embedding and the size of the embedding. And then this is the size of the number of features that you have. So K. And then this VR here is also it is a 2E by K So basically what you're doing is you're projecting into a k-dimensional feature space. You're taking a nonlinearity, and then you're multiplying that by a vector. So what this is doing is it's extracting features based on this bilinear function. Does that answer the question? So because of this, this actually has a bunch of features. It has this large feature vector, large feature matrix E by E, and then by K. So this is a powerful model, but perhaps over-parameterized. So at about the same time, there is a much, much simpler model. And this is caught on a little bit more, I think, perhaps because it's so simple. And the idea is that we want to learn relations from embeddings. And we want to try to learn a transformation vector that basically shifts word embeddings based on their relation. So this is much closer to the original intuition. So yeah, sorry I kind of messed up the explanation for the previous slide, but this is much closer to the intuition that we were talking about before. So the idea is that we learn a transformation vector that basically shifts word embeddings based on their relation. So we have H plus L, which means that we move, we take H, which is kind of the head, and T, which is the tail of the relation. And we add L to H and see how close it is to T. And then if T is close, then we assume that this relation holds, and if T is far, then we assume that this relation does not hold. And so we have this L for each relation that we want to be optimizing, and then we have a set of relations that we want to be optimizing over, HLT, and then we have a set of kind of distractor relations, which are the relations that, it's the set of things where the relation does not hold here. So you want to basically optimize a margin-based loss that says the ones that are actually in relations with each other get a better score than the ones that are not. And this method is often called trans-E, and the reason why it's called trans-E is because in embedding space you're translating you're translating the vector to get things to be close together. So this is exactly following the intuition of this thing here, where the red vector would be your vector L. So the thing to note here is that this is one vector for each relation. It's additive modification only. There's no multiplication anywhere in here. And it's intentionally much simpler than the neural tensor network just to reduce the parameterization. Yet it still performs quite well for a model this simple. However, there are a few very clear problems with this model. One very clear problem with this model is that there are you don't want to assume that all of the dimensions are relevant to a parameter, a particular relation. So let's say, to give a very simple example, let's say we want to find the capital. We want to find the capital of a city. Sorry, a capital city of a country. In the capital city of a country, knowing which country the city belongs to will be encoded in some particular elements of the vector, correct? But we'll also have other information like how big is the country. Ideally we would like to know how big a country is from its vector as well, and we would assume that maybe this would be relevant, etc. And it's very naive to assume that everything will be encoded precisely linearly in space. There will be other intervening factors that cause this problem. Another one would be something like Georgia, is a polysemous word where you have Georgia state and Georgia, the country. So because it's not realistic to assume that all the dimensions are relevant, the idea is pretty simple. Basically, you project the word vectors onto a hyperplane specifically for that relation, then verify the relation itself. So in the regular trans-Z model, here they renamed the R into the L into R. You're assuming that you go from H, the head, to T, the tail, and you follow the relation vector R. What this method does instead is first you project onto a new hyperplane, and then you follow the relation along this hyperplane. So the idea is this projection gets rid of all the information that's irrelevant to your decision whether a relation holds, and then you just measure it along the hyperplane that has the relevant information. Yeah.
These models does not take into account the context of like what kind of sentence they are in.
One thing that I maybe didn't say explicitly, but when we train the word embeddings are trained based on context. So the word embeddings themselves are assumed to already include information about.
Yeah, but in this case, the two given entities or two dimensions, they can only have one type of like relation distribution in
So that's a good question. So in the trans-Z model, actually that is, in the trans-Z model, let's say you have something like, hometown. You have something like hometown, and you have place where the person died, place of birth and place of death. And place of birth and place of death are very highly correlated. So it would be very common for them to be the same, but also for a lot of people, the place of birth and place of death is different. So if you assume that a vector, includes both the place of birth and place of death, for trans E, it would be very difficult to have both of those relations be able to be encoded, because basically you would need to use the same vector for both of those two relations and wouldn't be able to get rid of irrelevant information. But in the case of trans H, basically you're getting rid of the irrelevant information first, and then doing this transformation. So because you're getting rid of the irrelevant information for that particular relation, you could have multiple relations between two entities, and it would conceptually not be a big problem in this way. Any other questions? So these are really simple. These models are very easy to implement, much easier than much of the stuff that I talked about this time, once you have a knowledge base in hand. There's also other methods that are a little bit more complicated, but this kind of covers the main intuition things. So this is a paper by Chiza, who's sitting in the back looking at his computer, but it's a very nice paper. So you can ask him about it later if you want to know more. But the idea is basically, if you think about a knowledge base, it has many, many relations. And some of them are very sparsely annotated. So let's say for CMU, CMU's year of founding is a relatively sparsely annotated relation. So we would like to learn this relation, but learning a projection matrix or whatever for just this relation itself, you don't have enough training data to do that well. So the idea is basically you treat each relation as a mixture of concepts with a mixture vector A that allows you to interpolate between them. So the way the model works is right here. So your relation vector or your projection matrix D is basically, or I guess it's a projection tensor D. Or no, projection, yeah, sorry, matrix D. And you have the number of relations, or the number of mixtures, I guess, which we could call size of alpha. That's a little bit, you know, hand wavy, but size of alpha, then you have the size of your hidden embedding. And so each of these columns is a single kind of mixture component that you then combine together to get the actual projection that you want to do. So the idea is, if you have two similar relations, this mixture variable will look similar, and then just a few of the components will be a little bit different, explaining the difference between the relations. Yeah.
Is this like doing some sort of dimensionality reduction?
Yeah, basically. And it's kind of doing sparse dimensionality reduction as well, so most of the mixture components get to be 0. So the interesting thing about this is you get better results because you're reducing the number of parameters that you use. But the more interesting thing is you can also take a look at these, like which values are active in this mixture of concepts. And you can see things like the hypernym, the tail of the hypernym is equal to the head of the hyponym, which is something that we know is true, essentially, and vice versa. Similar to is a relation where you have heads and tails, and similar to is symmetric, so you can see the tail component and the head component are close together. So, yeah.
What's the intuition of what the concept like? Like, is there something specific that you know?
As far as I know, maybe you can elaborate, but I think the concepts themselves are not necessarily interpretable. It's more by looking at this that you can see which relations are close together and which ones are far apart. Is that a fair assessment?
Yeah.
Okay. Yeah.
So how is this sparsity enforced?
Yeah. So,
How sparse is the representation?
or how do you make it sparse?
We enforce zero sparse constraint. So instead of like against vector, we just pick at most k matrix out of P. And how do we select those k matrix? We do here there's some discrete variables like involving in the organization. So we do something like EM, where the one step we optimize the continuous timers using HCD. And in the other step we use like a greedy method to select those key components.
So there's also a lot of ways to kind of do sparsity in neural models that I could elaborate on later if necessary. But this is one example, and you can look up the paper for more details as well. Yeah. So I'll try to repeat as faithfully as possible. But basically, there's in EM, they're doing an L0 regularization, which means you have a penalty every time you have an extra one, and they do this by enforcing a hard constraint on the number that you have in running an EM-like algorithm to learn this. So. Okay, so another thing, this actually partly handles the thing that we talked about before with null and reverb, which is that you can learn relations from text directly as well. So this is basically identifying relations within text as opposed to learning from word embeddings. So distance supervision for relation extraction, this was covered in the reading, but given an entity relation entity triple, we want to extract all text that matches this and use it to train. So we get Steven Spielberg in Saving Private Ryan, which we know are in a director movie relation. And we extract all of this text and use it as supervised training data. And this creates a large corpus of noisily labeled text to train the system. There is a fair amount of work on doing this with neural networks. Maybe the first one is this relation extract classification with recursive neural networks. So they basically create a syntax tree and do a tree structured encoding, like we talked about in the previous classes. And then they classify the relation using the representations of both the minimal minimal constituent containing the words. So basically, this is what the encoding model looks like. They use something called the recursive matrix vector model, but it could probably also be a tree LSTM model as well. The most important thing is that what you do is you have Steven Spielberg's film Saving Private Ryan is kind of the minimal constituent that contains these two entities. So the representation of that clause, of that phrase, would be the thing that you feed into your relation classifier. So it's pretty simple. As long as you have this tree structured composition, it's basically it makes it into a classification problem. There's also methods using CNNs. So they extract features without syntax using CNNs, including the lexical features of the words themselves, features for the whole span between the words extracted using convolution, and then use these to do relation classification. So if we have people have been moving back into downtown, we have the word representations where we do things like sum of the word representations, and then we have a CNN over a window containing these entities. So it's a pretty straightforward model, but they show that this works well compared to the previous one. So then there's also joint modeling of knowledge-based relations in text. And the idea here is that basically we have multiple examples of these knowledge-based relations. So we have something like subject. If we have a dependency tree, we have subject, founder of, object. And we can calculate all of these over a big database, right? So we have two entities. We want to decide the relation between them. We have subject, founder of object, subject, co-founded object, etc. And we have the counts of all of these. And we can model the relations with the CNN, where we basically just run a CNN over this path. And this allows us to extract, extract features with a multi-layer perceptron. And then these can be aggregated over all of the things in the database, or all of the instances that you find in all of the text. So one very interesting thing about distant supervision type things is distant supervision is a really good way to get some supervised data, but we know that this data is going to be incorrect sometimes. Sometimes it's going to contain things that we don't that we know are incorrect. And this is a very nice paper from last year, where basically the idea is that there is noise in the distant supervision label, so we want to be able to model this noise. And the way this works is basically we have they call this a transition matrix. I would normally call this a confusion matrix. And the idea behind a confusion matrix is if you have predictions where you're maybe like 0.9% certain that the first one is correct, you're 0.1% certain that the second one is correct. You then have a matrix that says, okay, but when you thought the first one was correct, you were actually wrong when you thought the first one was correct, you were actually wrong 20% of the time. And when you thought the second one was correct, you were actually wrong 30% of the time. So we're going to take into account this confusion and project your answers into a new space that takes into account this confusion. So this is the idea here. So you make a prediction, and then you transform the probabilities of this prediction with a confusion matrix. And by controlling this matrix, we can adjust to the amount of noise expected in the data. So one good thing about this, this method is if we set this confusion matrix or transition matrix to the identity matrix, we're just doing normal training, right? So if it's the identity matrix, we do a transformation that doesn't do anything to our predictions and just keeps them as is. And so, so this is kind of a generalization of the normal training situation. So what they do is they use normalization of the trace of the matrix to try to make it as close as possible to identity. And then they also start training with no transition matrix on data expected to be clean, and then they phase in the transition matrix on the full data. So you could also imagine a thing where you have some subsets of data. You have a small subset of labeled data that you're pretty certain is correct. And then you have a large subset of distantly supervised data that you think might have noise in it, and you could learn different transition matrices for these, for example. So I think this is a pretty elegant solution to, kind of dealing with noisy data in these models. Any questions about this? Okay. So another thing we can do is we can learn from relations. So the idea is basically word embeddings give information of the word in context, which is indicative of knowledge-based traits. Also, other relations or combinations of them are indicative of whether a relation exists. So this is basically a link prediction problem in graphs. There's a lot more work on kind of graph modeling, so I'm not going to cover this super in detail because it's kind of moving to the border of the realm of natural language processing stuff. But just for completeness, you can do things like tensor decomposition, where basically you model relations by decomposing a tensor containing all of the entity relation entity tuples. And so this is actually similar to the thing that I talked about before, where we have latent factors or latent concepts in our relation extraction model. So this is saying if certain relations exist, then probably other relations will exist as well. So you do this by reducing the dimensionality, then increasing the dimensionality again until you have your full tensor of entity relations. Another kind of interesting thing is modeling relation paths. So multi-step paths can be informative for indicating whether we have individual relations. So this is an application that seems like it would be very useful for a lot of us. So let's say we're writing a paper in a new domain and we don't know where to submit it. So given the vocabulary of our paper, which conference should we submit to? And so basically what it learns is these rules on paths through the knowledge base, where we go from word to has title -1. So this jumps up to papers that have this title, have this word in the title, and then you jump back down to which journal this paper was in. And if a paper with this word in the title has been published in a particular journal, that's pretty indicative that we should be publishing there. And then you can extract all of these other things as well. Another thing kind of in this vein of optimizing things over paths is a method that basically does a similar thing to what we were talking about with trans-E. It steps to get it steps to basically transform relations into a new space, and then use this new space to infer what type of entity should be on the other end of that relation. But the simple idea here is that we would like to optimize so that after traveling along one of these paths, we still get the correct entity. So here's an example. So let's say we say Ted Lincoln. Where was Ted Lincoln's father born, or something like that, or where were Ted Lincoln's parents born? And so you make a single transformation to get a new vector. Then you get another. You do another transformation to get another vector. And the idea is, after you follow this path, you should arrive at Washington, D.C. So even if you make multiple steps along the path in the knowledge base in vector space, you should arrive to the correct answer, as we know is the correct answer via the knowledge base. So the interesting thing here is, in the results in this paper, they showed that, number one, unsurprisingly, if you optimize along the paths, you get a lot better at inferring multi-step relations. So you get a lot better at saying, at answering questions like where was, yeah.
Could you elaborate once more? What are they doing exactly?
Oh, okay. So T parents is a transformation matrix that says find this person's parents. T location is a transformation matrix that says find the location. I guess maybe it's saying not where they were born, but find where they lived or something like that.
So you're starting with some embedding for Ted Lincoln.
Yeah.
And matrix multiply across all of them.
Yeah, you do two matrix multiplies.
So once you do a matrix multiply, what happens to the nodes at Abraham Lincoln and so on and so forth? Do you discard them entirely, or what do you?
As far as I remember, they discarded them entirely and just optimized along the path there. They might have done both, but I think they just optimized along the path. So one of the good things about this model is it also greatly increases the amount of data you can use for training, because all of the relations in your data set, you have a certain number of relations in your data set, but you have many more paths. You have like almost, quadratically more paths. So if the average fan out of the average fan out of a node is n, then you have n squared paths, so you can increase the amount of training data. So unsurprisingly, the result here is, what the unsurprising result about this is you translate twice, and if you optimize for this, you get better at inferring multi-step paths. But the more surprising result is, if you do this, you get better at not only inferring multi-step paths, but also inferring single-step paths as well, probably just because you increase the amount of data that you have to train. This might also be interesting from other things that you could do with word embeddings, like multilingual stuff. But as far as I know, it hasn't been applied to applications here. So to take this full circle, there's also work on differentiable logic rules. In the this basically considers full paths, full paths through inferences in a differentiable framework. So the idea here is that you want to infer some sort of logical relation according to logic rules like has office in city, city and country, and whether this implies has office in country. So you treat the path as a sequence of matrix multiplies where the rule weight is A, and based on this, you basically multiply along these paths, and you can train it fully end to end. So the idea here is basically that you want to do this in a differentiable framework, like this. This is kind of neat. It seems like a good way to kind of infer weighted logic rules if you're interested in logic or or inference or something like that. Okay. Are there any questions about this? Okay. So now in the final part, this is not super long, but I'm just going to talk about using knowledge bases to inform embeddings. So this is going in the opposite direction. We have a big knowledge base, we have embeddings, and we want to make our embeddings better. So up until now, we were looking to make our knowledge base better using embeddings. So this is the opposite. And so one thing that people have done is lexicon-aware learning of word embeddings. So basically the idea is that we want to incorporate knowledge in the training objective of word embeddings. So similar words should be in close places in the space. So, sorry, I thought I had an equation on this slide, but I didn't. But basically, you have a two-part training objective, where one part of your training objective is whether, the word-to-vec training objective is basically whether a word t is close to its context words, t minus 1. Or t plus 1, or the context in t minus 1, t plus 1, etc. Right? So this is the standard word-to-vec training objective, but you add another part of the training objective where you want to say WT is also close to its synonyms in the knowledge base. So it's simple enough, but the good thing about this is, word embeddings are good if they're trained on lots and lots of data for each of the things you have, but WordNet is also very extensive. People have spent tens of years making WordNet extensive and having its synonym sets be good. So this is one good way to use this, and they show improved results on a number of tasks. So another thing that's also very useful is retrofitting of embeddings to existing lexicons, done by Manal Faruqui, who graduated from here. So this is similar to the joint learning method, but it's done through post hoc transformation of embeddings. So the big advantage of this, probably joint training is better if all things are held equal. You do it during the training process instead of post hoc. But the reality is, when Google trains your word-to-vec embeddings on the Google News corpus of 1,500 billion words or whatever, you probably don't want to be doing that every time you change your lexicon, right? So the idea here is basically you take the great 1,500 billion word trained embeddings and you transform them to match the lexicon that you're interested in. So this also has a double objective of making the transformed embeddings close to the neighbors and close to the original embedding. So it's as simple as you have the original embedding q hat I, and then you have all the neighbors of I in the knowledge base or in the lexicon, and you want to make those close as well. So then you optimize these. You have a beta term that trades off between the importance of each of these objectives. You can also use this to force antonyms to be away from each other. So one problem is that antonyms and synonyms tend to be very distributionally similar, so they get confused in word embeddings, and it's as simple as adding another objective for this. Yeah.
So is it to make the embeddings that are synonyms close to each other and the antonyms far away from each other?
Yeah, basically. Yeah. So you want to increase the distance between the antonyms and decrease the distance between the synonyms. So another piece of work that uses this idea of retrofitting embeddings to lexicons is multi-sense embedding. So the idea here is basically we create a model. So we take our existing word embeddings and we take our WordNet, for example, and WordNet has a whole bunch of different synonyms. Or a whole bunch of different senses for each word. And all of these are grouped into syn sets, which are basically sets of synonyms. So of course, Bush, the plant, in Bush, the president, will be in different syn sets. So they create a model where each of these different meanings is separated, and they either optimize this using EM or a hard EM example, where they suggest this is most, where they pick the sense that's most probable. So they have a way, they basically predict the sense from the context, and then from the context, from the sense, they predict the context. And there's also a retrofitting version of this method as well. I haven't written this on the slides, but you can also do this post hoc with already pre-trained embeddings. So I think from a very practical point of view, if you have entity embeddings, you have word embeddings, and you want to make them better, there are these big structured databases. So it's a very easy thing to do. We personally did the retrofitting thing for multi-sense embeddings, and it took us about half a day of work. So if you have some place where you're bothered because you have one embedding that's conflating a whole bunch of different senses, this is a good way to solve the problem relatively quickly. Yeah, that's all I have for today. Are there any questions? Yeah.
Is there any relevant literature on answering like normal questions using these knowledge bases?
Answering questions.
Like natural language questions.
Yes. So, kind of the whole field of semantic parsing is, which I think I'm actually going to talk about next week or something like that. Or no, wait. I already talked about it. No? Okay, I'm going to talk about it next week. Sorry, it's been a long semester. So yeah, I am going to talk about it very soon. And basically there's a couple ways you can do it. One is by embedding your knowledge base and then trying to match embeddings against the knowledge base. The other way is by creating some sort of symbolic query using a neural network and then executing that query against your knowledge base to get the answer and training it in a weekly supervised fashion, for example. Any other questions? No? Okay. Well, thank you very much then.